in this lecture I will answer two questions. In the first question we'll find out the area of this green shape in two different methods. And in the second question we'll find out the area of this circle that intersects with this right triangle ACP at those 2 points. So we'll start with the first question. In the drawing we have quarter circle AOB. This is side OB. This is equals to 2 units in its length. This is line 7 AD. This is equals to this line 7 DO. Again, our task is to find out the area of this green shape. The green shape, it is actually the right green triangle TCB because angle DCB equals to 90 degrees in its side. So we have to find out the area of this green right triangle DCB. So first of all, AOB is a quarter circle, and therefore this is angle AOB, that is a right angle. In addition, BO and OA, they are both the radius of this semicircle and of this quarter circle. The radius BO equals to 2, and the radius AO must be also equal to 2 units in its length. The radius AO that equals to 2. The radius AO has been bisected into 2 halves at point D. The first half AD equals to the length of the radius that is 2 over 2 is 1. The second half of the radius AO is DO, that is of course equals to 1 unit in its length. In the next step, we implement the Pythagoras theorem on this right triangle DOB. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT is abbreviation for Pythagoras theorem. In this right triangle DOB, according to the Pythagoras theorem, DB squared, that is the square of the hypotenuse, equals to DO squared plus OB squared. And again, according to the Pythagoras theorem, in this right triangle DOB, DB squared, that is the square of the hypotenuse, equals to DO squared plus OB squared. DB is the missing side, so we leave it as it is, so it is DB squared equals to DO squared. DO is 1, therefore DO squared is 1 squared, that is 1, plus OB squared. OB is 2, therefore OB squared is 2 squared, that is 4. So in total, we actually found out that DB squared equals to 1 plus 4, that is 5. So DB squared equals to 5. Here we take a root out of this equation and finally get that the length of the hypotenuse DB, is equal to the square root of 5 units. This is the hypotenuse DB, that is equal to the square root of 5 units in its length. In the next step, we will do a construction, that is to say, we will complete this quarter circle to a circle. So completed the quarter circle to a circle. And we will extend the radius BO by straight line until it touches the circle. And we will define the touching point of the extended radius BO with this circle. This point is point P. BO is the radius of the circle, and therefore it is absolutely a straight line. When you extend a straight line by straight line, the result BP is also a straight line. So BP is a straight line that touches the circle, those 2 points B and P, and therefore BP is a chord. BP is a chord that passes from point O, that is the center of the circle, and therefore BP is the diameter of the circle because of the fact that any chord that passes through the center of the circle must be the diameter of the circle. So chord BP is the diameter of this circle. Point O is the center of the circle, point P is the point of the circle itself, therefore P is the radius of the circle, is equals to 2 units in its length. The next step, we will extend the radius AO by straight line until it touches the circle. And we will define the touching point of the extended radius AO with this circle. This point is point Q. AQ is also the diameter of the circle, exactly for the same reason that PB is the diameter of the circle. So write it down, AQ is the diameter of the circle. Point O is the center of the circle, point Q is the point of the circle itself, therefore OQ is the radius of this circle, that is equals to 2 units in its length. In the next step, we will extend the radius CD by straight line until it touches the circle. But the question is where the extended side CD will touch the circle. We will assume that the extended side CD will touch the circle at this point, point N. So, first of all, I present to you rule 5. According to rule 5, any peripheral angle that is equals to 90 degrees in size must subtend on the diameter of the circle. In the drawing we have a circle. This is peripheral angle MAN that is equals to 90 degrees in size, and according to this rule 5, peripheral angle MAN must subtend on the diameter of the circle. Peripheral angle MAN subtend on chord MN, that is the diameter of this circle. So according to this rule 5, any peripheral angle that is equals to 90 degrees in size, like this peripheral angle MAN must subtend on the diameter of the circle. So we can implement rule 5 in our drawing. So according to our assumption, the extended side CD touches the circle at this point, point N. So in the drawing we have peripheral angle BCN is equal to 90 degrees in its size according to what is given as the question. And according to rule 5, any peripheral angle that is equal to 90 degrees in size must subtend on the diameter of the circle. But peripheral angle BCN that is equal to 90 degrees in size subtend on this chord NB. This is chord NB. Chord NB is definitely not the diameter of the circle because of the fact that it doesn't pass for point O, that is the center of the circle. Any chord that doesn't pass for the center of the circle cannot be the diameter. So it is contradiction to rule 5 because we have peripheral angle BC and is equal to 90 degrees inside, and still it doesn't subtend on the diameter of the circle. So due to the contradiction to rule 5, we will conclude that the extended side CD cannot touch the circle at this point N. In the next step, we will assume that the extended side CD will touch the circle at this point M. So according to our assumption, we have peripheral angle BCM that is equal to 90 degrees inside, and therefore according to rule 5, peripheral angle BCM must subtend on the diameter of the circle. But in fact, peripheral angle BCM subtend on chord BM. Chord BM is definitely not the diameter of the circle because of the fact that chord BM doesn't pass through point O, that is the center of the circle. Any chord that doesn't pass through the center of the circle cannot be the diameter of the circle. So we have here contradiction to rule 5 because we have peripheral angle BCM that is equal to 90 degrees inside, instead it doesn't subtend on the diameter of the circle because chord BM is definitely not the diameter of the circle. So due to the contradiction to rule 5, we conclude that the extended side CD will not touch the circle at this point M. And therefore, we will conclude that the extended side CD will touch the circle at point P and not in any other point. Otherwise, we will have contradiction to rule 5. Now we don't have contradiction to rule 5 anymore. Why? Because of the fact that this is peripheral angle BCP. It is equal to 90 degrees inside, and indeed peripheral angle BCP subtend on chord PB, that is the diameter of the circle. Exactly according to rule 5. PB is the diameter of the circle, so PB is the diameter, it is absolutely a straight line. So if you focus on the upper side of the straight line PB at point O, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 says that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of the straight line PB at point O? We have this angle that is a right angle, plus this missing angle, in total the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore this missing angle must be equal to 90 degrees at this size. This is the right triangle PDO. In this right triangle PDO, PD equals to 2, DO equals to 1, and therefore the hypotenuse PD must be equal to the square root of 5 units in its length. Two square plus 1 square is 5, so PD square equals to 5, and therefore PD equals to the square root of 5 units in its length, according to the Pythagoras theorem, of course. So here we will implement rule 24 in our drawing. So I repeat quickly on rule 24. According to rule 24 is true in any circle. So in any circle, if chord AB intersects with chord CD at point O, then the following equation is true. AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. So in the drawing, we have a circle. This is chord AB that intersects with chord CD at point O. So whenever we have two chords that intersect with each other inside the circle, then the following equation is true. That AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. So we can actually implement rule 24 in our drawing. Why? Because in our drawing, This is chord AQ. Chord AQ is the longest chord in the circle because it is the diameter. Chord AQ intersects with this chord CP at point D. Again, chord AQ intersects with chord CP at point D. Why CP is a chord? Because of the fact that we extended the side line CD by side line. When we extended side line by side line, the result CP is a side line. So CP is a side line that touches the circle those 2 points C and P, therefore CP is a chord. So in total, we should find out that chord AQ intersects with chord CP at point D. So all the requirements of rule 24 are satisfied, and therefore we can implement rule 24. All the requirements of rule 24 are satisfied, and therefore we can implement rule 24. So I write it now. Chord AQ intersects with this chord CP at point D. The intersection point of chord AQ with this chord CP occurs at point D. So all the requirements of rule 24 are satisfied, and therefore we can implement here rule 24. And again, chord AQ intersects with chord CP at point D. So according to rule 24, the following equation is true. That AD times DQ equals to CD times DP. AD times DQ equals to CD times DP. And again, according to rule 24, the following equation is true. AD times DQ equals to CD times DP. AD is 1 times DQ. DQ in total equals to 1 plus 2, that is 3. And it is equals to CD. CD is the missing side, so we leave it as it is. Times DP. DP equals to the square root of 5 units in its length. So in total, we should find out that according to rule 24, 1 times 3 equals to CD times square root of 5. 1 times 3 is 3, so 3 equals to square root of 5 times CD. Here we will divide this equation by square root of 5, and find here that the missing side CD is equal to 3 over square root of 5 units in its length. This is the missing side CD is equal to 3 over square root of 5 units in its length. In the next step, we will implement the Padas theorem in this right green triangle DCB in order to find out the missing side CB. Here by PT is evaluation for Padas theorem. according to the quadratic theorem, in this green right triangle DCB, dB squared, that is the square of the hypotenuse, is equal to CD squared plus CB squared. And again, according to the quadratic theorem, in this right triangle DCB, the following equation is true. dB squared, that is the square of the hypotenuse, equals to CD squared plus CB squared. dB equals to the square root of 5, and therefore dB squared equals to the square root of 5 squared, that is 5. And it is equals to CD squared. CD equals to 4 over square root of 5, and therefore CD squared equals to 4 over square root of 5 squared, that is 9/5. Plus CB squared. CB is the missing side, so we leave it as it is. So it is plus CB squared. So in total, we should now know that 5 equals to 9/5 plus CB squared. Here we multiply 5 by 5, and then we divide it by 5 in order to come out with this number. 5 times 5 is 25 over 5. 25 over 5 is of course equals to 5. And it is equals to 9/5 plus CB squared. Here we will subtract 9/5 from this equation and find again that 25 over 5 minus, or 25/5 minus 9/5 is 16/5, and it is equal to CB squared. Here we take a root out of this equation, and we finally get that the missing side CB is equal to the square root of 16, that is 4 over square root of 5. Because again, we should know that this is the missing side CB, that is equals to 4 over square root of 5 units in its length. Now it is very easy to find out the area of this green shape. Because the green shape, it is actually the green right triangle DCB. So actually you have to find out the area of this green right triangle DCB. So write it down. The area of the green shape is actually the area of the right triangle DCB. And the area of the right triangle DCB, the area of this right triangle DCB equals to the base DC times the height CB over 2. And again, the area of this green right triangle DCB equals to the base of the triangle that is DC times the height that is CB over 2. The base DC equals to 4 over square root of 5 units in its length times the height CB, that is equals to 4 over square root of 5 units in its length divided by 2. So in total, we should now know that the area of the green right triangle DCB, that is actually the area of the green shape, equals to the value of this expression. What is the value of this expression? Here we have 3 times 4, that is 12, over square root of 5 times square root of 5 is 5, over 2. So in total, this expression equals to 12 over 5 over 2. Here we will move 2 to the denominator, and get that this expression in total equals to 12 over 5 times 2. So it is 12 over 5 times 2. 5 times 2 is 10. So the area of the green shape equals to 12 tenths. This is actually 1.2 square units in size. So actually, we found out that the area of this green shape, that is the area that we are looking for in this question, it is equal to 1.2 square units in size. So we finish with the first method. The next step I'm going to have to find out the area of this green shape according to the second method. AOB is a quarter circle, therefore this is a right angle. OB and OA is above the radii of this quarter circle. This equals to 2. So the radius AO must be also equal to 2 units in its length. The radius AO has been bisected into two halves at point D. The first half AD must be equal to the radius over 2. So it's 2 over 2, that is 1. And the second half must be also equal to 1 unit in its length. In the next step, we will complete this quarter circle to a semicircle. And we will extend the radius BO by straight line until it touches the semicircle. We define the touching point of the extended radius BO with this semicircle. This point is point P. BO is the radius of the semicircle. It is absolutely a straight line. When you extend the straight line by straight line, the result BP must be also a straight line. So BP is a straight line that touches the semicircle at those two points B and P. Therefore BP is a chord. Any straight line that touches the circle at 2 points, it is defined as a chord. So BP is a chord that passes through point O, that is the center of the semicircle, and we know that any chord that passes through the center of the circle or semicircle must be the diameter of the semicircle or circle. So PB is the diameter of the semicircle. We only found out that PB is the diameter of the semicircle in the first method, but repeated on the same explanation. So PB is the diameter of the semicircle. Point O is the center of this semicircle. Point P is the point of the semicircle itself. Therefore, OP is the radius of the semicircle. This is equals to 2 units in its length. In the next step, we will extend side CB we extend side CD. It is one side of this triangle DCB. So side CD is one side of a triangle. It is absolutely a straight line. We will extend the side CD by straight line until it touches the semicircle. We already found out in the first method that the extended side CD must touch the circle or semicircle at point P and not in any other point due to the contradiction to rule 5. So the extended side CD must touch the semicircle at point P according to what I already explained in the first method. Now, when the extended side CD touches the circle at point P, we don't have any more contradiction to rule 5. Why? Because we have triangle BCP, this is equal to 90 degrees in its size according to what is given in the equation. According to rule 5, any triangle that is equal to 90 degrees in size must subtend on the diameter of the circle. And indeed, triangle BCP is equal to 90 degrees in its size, subtend on chord PB, that is the diameter of the semicircle, exactly according to rule 5. want to explain in the first method that this is angle AOP, that is the right angle according to rule 3, so I'll not repeat on the same explanation. So in the right triangle PDO, the hypotenuse PD must be equal to the square root of 5 units in its length, because 2 square, that is 4 plus 1 square, equals to PD square. So PD square equals to 5, and therefore PD equals to the square root of 5 units in its length. According to the Pythagoras theorem, of course. In the next step, we will define this angle DPO as alpha. So in this right small triangle PDO, this angle equals to alpha, this angle equals to 90 degrees, therefore this first missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees, that is the sum of the angles in any triangle. Likewise, in the big right triangle PCB, this angle equals to alpha, this angle equals to 90 degrees, and therefore this first missing angle must be equal to 90 degrees minus alpha, according to the sum that states that the sum of the angles in any triangle is equal to 180 degrees. It is very easy to see that this is the small right triangle PDO is similar to this big right triangle PCB. So why those two right triangles are similar to each other? Why the small right triangle PDO is similar to this big right triangle PCB? First of all, this is the angle alpha. That is a common angle that belongs to both triangles. So we can find out that angle alpha equals to itself is a common angle that belongs to both triangles. Likewise, those two angles are both equal to 90 degrees, and therefore they are equal to each other, and finally those two angles are both equal to 90 degrees minus alpha, and therefore they are equal to each other. So I should find out that all the three angles of this right triangle PDO are equal to all those three angles inside this right triangle PCB. And therefore those two right triangles are similar to each other according to angle similarity rule. So right now, this is the right triangle PDO, the right small triangle PDO, and similar. This is the sign of similar to this big right triangle PCB, according to angle similarity rule. Okay, again, if you found out that the small right triangle PDO is similar to the big right triangle PCB according to angle similarity rule. And from the fact that the right small triangle PDO is similar to the big right triangle PCB, we derive that the following relationship exists between their sides. We derive that side PD of this small right triangle PDO over side PB of this big right triangle PCB is equal to side DO of this small right triangle PDO over side CB of this big right triangle PCB, and it is also equal to side PO of this small right triangle PDO over side C over side PC of this big right triangle PCB. So write it down. PD over PB equals to DO over CB, and it is also equals to PO over PC. So repeat again, from the fact that the right small triangle PDO is similar to the big right triangle PCB, we will derive that the following relationship exists between their sides. We will derive that side PD of the small right triangle PDO over side PB of the big right triangle PCB equals to side DO of the small right triangle PDO over side CB of the big right triangle PCB, and it is also equals to side PO of the small right triangle PDO over side PC of the big right triangle PCB. PD equals to the square root of 5 over PB. PB in total equals to 2 plus 2, that is 4. This is the diameter of the semicircle. This is equals to 4. And it is equals to DO. DO is 1 over CB. CB is the missing side, so we leave it as it is. And it is equals to PO. PO equals to 2 over PC. PC in total equals to square root of 5 plus DC. So in total, we actually found out that square root of 5 over 4 equals to 1 over CB equals to 2 over square root of 5 plus DC. Those two sides of this long equation are equal to each other. Therefore, we get equation 1 from those two sides that are equal to each other. So according to equation 1, we will get that the square root of 5 over 4 equals to 1 over CB. So write it down. According to equation 1, we can find out that square root of 5 over 4 equals to 1 over CB. Here we first multiply this equation, equation 1, and get that according to this equation 1, 1 times 4 is 4, equals to the square root of 5 times CB. 4 equals to the square root of 5 times CB. Here we will divide this equation 1 by square root of 5. We get that according to this equation 1, CB equals to 4 over square root of 5 units in its name. This is the missing side CB. This is equals to 4 over square root of 5 units in its length. We continue to focus on this long equation. Those two sides of the equation are equal to each other, therefore we get the equation 2 from those two sides that are equal to each other. So according to equation 2, we get that the square root of 5 over 4 equals to 2 over square root of 5 plus DC. So I write it down. According to equation 2, square root of 5 over 4 equals to 2 over square root of 5 plus DC. So here we cross multiply this equation 2, and get that according to this equation 2, 2 times 4 is 8, and it is equals to the square root of 5 times square root of 5 plus DC. And again, according to equation 2, I shall find out that eight equals to the square root of 5 times square root of 5 plus DC. So 8, according to equation 2, 8 equals to the square root of 5 times square root of 5 is 5, and plus square root of 5 times DC. So here we subtract 5 from this equation 2, and get that according to equation 2, 8 minus 5 is 3, so 3 equals to the square root of 5 times DC. Here we will divide this equation 2 by square root of 5, and find again that according to this equation 2, DC, that means inside DC is equal to 3 over square root of 5 units in its length. This is the means inside DC that is equal to 3 over square root of 5 units in its length. Now it is very easy to find out the area of the green shape. The area of the green shape, that is the area that we are looking for in this question, is equal to the area of this green right triangle DCB. And again, the area of the green shape is equal to the area of the green right triangle DCB. And the area of this green right triangle DCB is equal to the base of the triangle that is DC times the height that is CB over 2. Repeat again. The area of this green right triangle DCB in total it is equal to the base DC times the height CB over 2. The base DC equals to 3 over square root of 5 units in its length, times the height CB is equal to 4 over square root of 5 units in its length, divided by 2. So in total, we should find out that the area of the green shape is equal to the value of this expression. What is the value of this expression? And in the numerator we have 3 times 4, that is 12, over square root of 5 times square root of 5 is 5, over 2. So in total the area of the green shape equals to 12 over 5 over 2. Here we move 2 to the denominator, and get that this expression in total equals to 12 over 5 times 2. So it is 12 over 5 times 2. 5 times 2 is 10. 12 over 10 is 1.2 square units in its size. So in both methods, we actually found out that the area that we are looking for in this question, that is the area of this green shape, is equal to 1.2 square units in its size. So we finish with the first question. The next step, I present you the second question, and we'll solve the second question of this lecture. In the second question, our task is to find out the area of this circle. So in the drawing, we have a circle that intersects with this right triangle ACB at those 2 points. In addition, you know that this is line segment BC, this equals to 1 unit in its length. This is line segment CP, this equals to 4 units in its length. This is angle ACP, that is the right angle, and therefore triangle ACP is the right triangle. And in addition, this is point P, that is a common point from this common point, common standpoint. This is a common standpoint in relation to this circle. From this common standpoint, point P, we have 2 tangents to this circle, tangent PA and tangent PB. According to rule 2, they are equal to each other. So I repeat quickly on rule 2. According to rule 2, the lengths of 2 tangents from a common standpoint to a circle are equal. So in the drawing, we have a circle. This is the common standpoint, point P. From this common standpoint, point P, we have 2 tangents to this circle, tangent PA and tangent PB. And according to this rule 2, they are equal to each other in their lengths. That is to say the length of tangent PA is equal to the length of this tangent PB, or PA equals to PB. So we can actually implement all two in our drawing. When put in our drawing, this is the common standpoint point P. For this common standpoint point P, we have two tangents to this circle, tangent PA and tangent PB. In the following, and tangent PB. In the following, all two are equal to each other. That is to say, PA equals to PB. So we write it down. So if we focus on this common standpoint point P, we have two tangents to the circle, tangent PA and tangent PB, and the following two are equal to each other. This is to say PA equals to PB according to all two. And again, according to all two, tangent PA equals to tangent PB in its length. But it is given us the question that the length of this tangent PB in total is equals to 4 plus 1, that is 5. So we can write here that PB equals to 5. And from this equation, PA equals to PB equals to 5. We will derive that tangent PA is also equal to 5 units in its length. So hopefully, this is tangent PA is equal to 5 units in its length. In the next step, we will implement the Pythagoras theorem on this right triangle ACP. Here by PT is the promotion for Pythagoras theorem. This right triangle ACP, according to the Pythagoras theorem, AP squared, that is the square of the hypotenuse, equals to AC squared plus CP squared. And again, according to the Pythagoras theorem, this right triangle ACP, the following version is true. AP squared, that is the square of the hypotenuse, equals to AC squared plus CP squared. AP is 5, and therefore AP squared is 5 squared, that is 25. And it is equals to AC squared. AC is the missing side, so we leave it as it is. So it is AC squared plus CP squared. CP is 4, therefore CP squared is 4 squared, it is 16. So in total, we actually found out that 25 equals to AC squared plus 16. Here we will subtract 16 from this equation. And finally get that 25 from 16 is 9, so 9 equals to AC squared. Here we will take a root out of this equation and finally get that the missing side AC is equal to the square root of 9, that is 3. The missing side AC equals to 3 units in its length. This is the missing side AC, is equals to 3 units in its length. PB is a tangent to the circle at point B. So PB is a tangent, it is absolute straight line. So if we focus on the upper side of the straight line PB at point C, here the sum of the angles must be equal to 180 degrees according to all three. So which angles we have at the upper side? On the upper side of the straight line PB at point C, we have this angle that is the right angle, according to what is given in the question, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to all three. Therefore, this missing angle must be equal to 90 degrees in its size. In the next step, we will define the center of this circle. This point is point O. And we'll define the radius of this circle as x. So the radius of this circle equals to x according to our definition. And we'll join points O and B together by a straight line. Point O is the center of this circle, point B is the point of the circle itself, therefore OB is the radius of this circle, is equals to x according to our definition. The radius OB is equals to x, the radius OB is drawn to point B, that is the point of tendency of tangent PB with this circle. Whenever your radius is drawn to the point of tendency, then tangent PB will be perpendicular to the radius BO. If PB is perpendicular to BO, it means that this angle equals to 90 degrees according to rule 1. In the next step, we will do a construction, that is to say, from point O, we will draw perpendicular on side AC. Again, from point O, that is the center of this circle, we will draw perpendicular on side AC. So actually, this angle equals to 90 degrees in its size, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and side AC. This point is point M. By doing this construction, you can do quadrilateral OMCB. Inside quadrilateral OMCB, we have 1, 2, 3 rectangles. The sum of 3 rectangles is 270 degrees. So 270 degrees plus the size of this fourth circle, in total they must be equal to 360 degrees according to the rule that says that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this fourth circle must be equal to 90 degrees in its size. So in quadrilateral OMCB we have 4 rectangles, and therefore quadrilateral OMCB is a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle OMCB, side BC must be equal to the opposite side OM. But BC is 1, therefore the opposite side OM must be also equal to 1 unit in its length. Likewise, according to the sum rule, in the same rectangle OMCB, side OB must be equal to the opposite side MC. But OB is x, therefore the opposite side MC must be also equal to x units in its length. What is the length of this missing line 7? Line 7 AM. From the drawing, it is very easy to see that AM in total equals to AC minus MC. Again, AM equals to AC minus MC. So, until now, the length of the short line 7 AM is equal to AC minus MC. So, AM in total equals to AC, that is 3, minus MC, that is equals to x. So, in total, AM equals to 3 minus x units in its length. This is the short line 7 AM. This is equals to 3 minus x units in its length. In the next step, we will join points O and A together by a straight line. Point O is the center of this circle, point A is the point of the circle itself, therefore OA is the radius of this circle, is equal to x. The next step, we will implement the Padas theorem on this right rectangle AOM.